Okay, so for 2.4, I need to make some corrections. Okay, enter key. All right, so let me see where that is. The last example now. Yes, it is 2. Yeah, these two just keep coming late. Right here, this example 3. Okay, so I need to make some corrections. Let's go down to here. You supposed to use the absolute value around the v. All right, because we don't know what v is. V could be negative. All right. Okay. For the x and the y, because that is the original problem. So when in the original problem you have ln of x and ln of y like this, that means we know that x and y are positive. Otherwise, the equation would be invalid. Okay, so we know that, but we don't know anything about v. All right, so we want to make sure that we always take the ln of a positive number. So we put absolute value around. So please make that correction. So you go down here, that is another one. Okay. And then right here. All right. And then the next one is right here. And then go to the right. You have it right there. Okay. And also right here. Right there. So for this step, 1, 2, 3. And in calculus 1, we know that the derivative of ln of the absolute value is 1 over that. Okay, so the absolute value doesn't affect the derivative. So you have so that integral would be the ln of the absolute value of u, right? That's u. Okay, so that's why you put the absolute value. So right here, you need to put absolute value around the v also. So right here around the v, absolute value again. And then when you exponentiate both sides, these cancel out. So you have this. And then to get rid of the absolute value on the outside, you put positive negative here. So that will give you this, right? Okay. So at this step right here, remember, this is what I did. But I went over, so well, this looks, too cumbersome. So that's not good. So I go ahead and okay. Oh, wait. Oh, I accidentally, hang on, okay. I didn't mean, I need to remove 2 students. I don't see profile pictures, so I don't know who they are. Oops. Yeah, so, like, yeah, they really waste the class time. Even students should know better than that, because when I see students with no profile picture, I just don't want to take a risk at meeting them into the Zoom meeting. Okay. All right. So right here, I have to keep. Okay, next time if you are not admitted into the room, then you know that you have to check and make sure that you have your profile picture. Okay. So I told the class already, you have to log into your Zoom account first before you use my link. Okay, so with all of the stuff that we did last time, I redid the problem. So this is not a good way. So there's a better way. So it's not wrong. Okay, it is not wrong, but I like to cross this out. Okay, so you can just cross that out. And then from here, from this step right here, you go to the right and you take a picture of that. See, it is much better. And here's the reason why, because you know that I was trying to find out what V was, right? But that is unnecessary because you know that your goal is to get the solution in terms of X and Y. So as soon as I get to this step right here, I can go ahead and replace V with X and Y, right? And then from here, I can just use the initial condition to find out what C is. And then once you know what C is, you can just go back and replace C with negative E. So you have your answer. Okay, so you have your answer right there. All right. So that is the implicit solution of that IVP. Now, the only time when you need to find out what that V is when I ask you to find a V. Okay, but here I didn't ask you to find a V. I asked you to solve by substitution. So you just use that appropriate substitution and you go down here and you do something so that in the end, your answer has an equation that has X and Y, and then that should be enough. Okay. So did you take a picture of that or? Okay, and then I will go to the next topic. All right. Okay. Now again, this is not wrong. Okay. What I'm saying is this is better. I just did this, and that's better than all the work that we spent on this one. All right. Now let's go to the next type, which is Bernoulli's equation. Okay. And Bernoulli equations have the form. So let's look at the general form. So here's the general form of a first order linear differential equation. And of course, if you divide both sides by a sub 1 of x, then you have standard form, right? Okay. So right here, that would be the standard form when you divide both sides by a sub 1, all right? Now, when you have that, and then on the right-hand side, see on the right-hand side of the general form, you have the dependent variable y, because so you have to be able to identify in the differential equation which variable is independent and which variable is dependent. Okay, so in this case, the dependent variable is y, and then on the right hand side you have that dependent variable raised to the nth power, whatever that n is. It could be any number. All right, then we call that equation a Bernoulli's equation. In standard form is this, and then you on the right side you have the dependent variable y raised to a power multiplied by that. Then that we call that a Bernoulli's equation. So when you have a Bernoulli equations, this is the substitution that you want to make. All right, okay, to solve that equation. So when you see y raised to a power on the right side, then you let u be y raised to 1 minus whatever that power is. So let's do example 4 so you can see what I'm talking about. So in example 4, you have this equation. Now the question is this equation a Bernoulli's equation? Can you tell me?
Yes, it is.
Yes, okay. So what make you think so?
Well, I mean, I'm thinking no. Wouldn't you need to move the x first and divide both sides by x?
You don't need to. You can have it this form or that form.
Oh, okay.
So what do you think?
Because of the y square on the right.
Because of the y square. Very good over here. All right, because of the y square. All right, so what is n in this case?
N equals 2.
N is 2, so that is n. Oh, that color doesn't look good. So n is 2. Okay, so from here you know that n is 2. So you know that n is 2. So you would let y be, so from this stage, you can either divide both sides by x first, or just leave it like this and make the substitution, and then later on you can do it. Okay, so it doesn't really matter. All right, but now you know the important step is you have to know what kind of substitution you need to make. So in this case, you let u be y raised to 1 minus n, which is n is 2, right? N is 2. Yeah, so n is 2. So you plug it in. So that gives you y u equals y to the negative first, or it is this. Okay, so that means y is equal to 1 over u. Now the reason why we do that is so we can find out what dy, what the derivative of y is, and so on. Okay, so once you have that, then what is the derivative? So dx dy dx is equal to the derivative of 1 over u with respect to x. All right, so that gives you negative 1 over u squared du dx. Okay, so now you can make your substitution. So now from here, you have x dy dx. Dy dx is negative 1 over u squared du dx minus 1 plus x. And then y is equal to 1 over u, right? So y is equal to 1 over u equals x times y squared, which is 1 over u squared. So after the substitution, that's what you have. So now let's see what we have here. Okay, so if you want to get rid of if you want to write it in standard form, so now you're going to have your equation in your differential equation is in du dx, not dy dx anymore, right? So you want to write it in standard form. That means you want to get the du dx by itself. Okay, so you need to move this, multiply this to both sides. So you multiply the reciprocal of this, which is negative u squared over x. Does it make sense? Now you might ask, how come we did not divide both sides by x to change that into standard form first? Well, you could do that, but if you did that, then later on you'd converted everything into u, then you still have something in front of the du dx, so you have to do it one more time. So why waste time doing it twice, right? So that's why you wait into this step, and then you multiply both sides by negative u squared over x to both sides. Okay, so you multiply to the left-hand side, which is negative x over u squared du dx. And then right here you have minus 1 plus x over u. Okay. And then on the right side, you multiply the same thing. So what you have is x over u squared. So I'm using parentheses. Okay, so I just want to make a note over here. So I make a note to myself that I'm writing this one in standard form. Okay, in standard. In standard form, I just abbreviate. Okay. All right. So after you simplify, so now you multiply out and simplify. What you have. So this, what you have is just du dx. And then what you have is plus 1 plus x all over x u. And on the right-hand side, you get -1. Okay? So that's what you have. Okay, so that is in standard form. So if you have so in this case, ask yourselves, okay, can I solve this equation by separating the variables? Okay, so maybe it's too complicated, but I noticed that this one looks like the derivative, and this is p, right, and this is q. So I use integrating factor. Okay, so I'm gonna use. So I'm gonna find an integrating factor. So this implies integrating factor. Mu of x is equal to e raised to the integral of p of x dx, where p of x is 1 plus x all over x. That's what p is. Okay, so that's what I have. Okay, so let's find out what that is. Okay, so let's do this first. So the integral of p of x dx is the integral of 1 plus x all over x dx. All right, so what you have is ln of the absolute value of x plus the integral of 1 is x, and then plus a constant c, right? But you know, we want to find an integrating factor, so we want to let this one be 0. Okay, so you know the integral is just ln of absolute value of x and so on. Okay, so now, so mu, so mu of x is e raised to the integral of p of x, which is ln of the absolute value of x plus x, which is e to the ln of the absolute value of x times e to the x, which is the absolute value of x times e to the x. But to get rid of the absolute value of x, you have to have a positive and a negative. Okay, now, so you have two options here. You could use mu equals the positive x e to the x, or mu equals negative x e to the x, right? We can just pick one. Okay, all right, we can just use this. Okay, so are all of you following that? Okay, we are trying to just use to find an integrating factor. Well, there are two choices here. We just pick one and pick the simpler one, which is the positive one. All right, so mu of x is equal to x e to the x. All right, so we just solve that equation by using So this equation becomes mu, right? So you multiply mu to both sides. So you multiply mu of x to the left-hand side, which is du. So this is a good review of section, I believe it's 2.3. And then on the right-hand side, you have mu of x times -1. So you have like -1 times mu of x, okay? All right, so what do you have? So from the method of integrating factor, when you multiply that integrating factor to both sides, then the left-hand side becomes the integral of mu of x times the function u. And on the right-hand side, you have mu of u, mu of x. Okay, and then you just integrate both sides. Okay, so you integrate both sides with respect to x. So from here, you integrate that with respect to x. Let me just write. With respect to x. And on the right-hand side, you integrate a negative mu of x with respect to x. All right, so what do we have? So on the left-hand side, what you have is mu of, so you cancel out the integral and the derivative. Okay, so you have mu of x times u, and mu of x is x e to the x times u. And on the right-hand side, you have the integral of negative x e to the x. I'm going to take the negative sign out. Okay. Let me move this to the left so I can save some space. Now on the right-hand side, that is integrating by parts. Okay, so you can just go to the right side and do some scratch work on that. Yes?
Excuse me, when you put the q of x, isn't there supposed to be a minus sign for all of them?
Where?
On the right side in purple.
Right here?
Yes,
Yes,
right.
right here should be negative. Yeah, thank you. Should be negative right here. Yeah, I missed that negative sign. Should be negative. That's the only place I missed, right? Okay, so here you let u. So you let u be, no, we don't want to use u. Okay. How about let's use u star be x and dv star be e to the x dx. So that means du star is equal to dx and v star is equal to e to the x. So you know the integral. So the integral of x e to the x dx is equal to u star v star. So I'm doing this as a review for you. And then minus v star du star. So what is that? That is x e to the x minus the integral of v star, which is e to the x dx. Okay. So you have x e to the x minus e to the x. And then, of course, you're going to add a constant. Okay. You need to add a constant, right? So, all right. So let's go back here and plug it in. So right here, you have x e to the x u equals negative. So it's going to be negative x e to the x plus e to the x plus c. So what is u? You divide x e to the x both sides. So you have negative 1 plus 1 over x plus c over x e to the x. Okay, so u is 1 over y, or y is 1 over u, right? So y right here, y is 1 over u. So you just simply combine all of these right here. Okay, so let me write. Let me write. Okay, so let me separate these. I guess you can write over here, okay, equals, and you combine all of these into one fractions, but I'm gonna do it over here, okay, and then I just move down a couple lines. So I combine these, so the LCD is x e to the x, so this is negative x e to the x plus e to the x plus c all over x e to the x. Okay, so what is y? So I guess I'm going to move down. 1, 2, 3. Okay, so what is y? So y is equal to 1 over u, implies y is equal to x e to the x all over, and then you can write c minus plus e to the x minus x e to the x, and then you have your answer. All right. Okay. Any questions so far? So again, if you made an appropriate substitution, then that would lead you to an easier differential equation for you to solve. In this case, it led to a differential equation in standard form, and then we use integrating factor to solve. Okay. All right. Okay. Now let's go to the last topic, and in this case, it is. Let me move this one up a little bit. It doesn't allow me to help out this. Okay. So now you have dy dx equals a function in terms of this. So whatever you think the inner function, so this is like a composite function. So and this is the inner function, whatever the inner function is, you let u be that. So in this case, you would let u be ax plus by plus c, okay? So for example, 5, you have dy dx. So it looks like this. And on the right side, your function f is the sine function. So this is a sine function of this function. So that is your inner function right there. So that's what you want to let u be. Okay. All right. So that's your u. That's what you want to be. So let me go to the book and look at some problems in there and see if you can identify the u. Okay. Okay. All right. Like this one right here. Okay. So what kind of substitution would you make? What is u for number 20 for problem 23?
X plus Y plus 1.
Good. How about 25?
X
X
plus Y.
plus Y.
X plus y. How about 27?
Y minus 2
Y
x
minus
plus
2 x plus 3.
There you go. Okay, so if you can identify the u, then then you know, after that it's just a matter of time. 28.
X plus
Y minus
no,
X plus
Y
Y.
minus X
Y
plus
minus
Y.
x plus y. Good. And now 26. That's what
X plus Y.
we're doing,
X
right?
plus
So
Y.
now 24. What do you think?
Is the whole thing?
No, not the whole
X
thing.
plus Y.
X plus y. Because this one is like 1 minus and then x plus y inside parentheses. Yeah, so you let u be x plus y. Now it you know, it wouldn't hurt if you try. So you let u be something and you work it out. It doesn't work, then you go back and make change your u, right? So you know, if you make a mistake, that's okay. It's a waste of time, but you learn from your mistake. So when you make a mistake and you spend quite some time to try to do the problem and you get it wrong, then that mistake is going to stick in your head for a long time. And it's good because when you make a mistake, it reminds me of next time when you see something like that is, hey, I'm not going to do that again. Okay. All right. So in this case, you're going to let u be y plus x. So let's do that and see what happens. Or x plus y. Okay. So if u is equal to x plus y, then you want to, so basically you want to turn this differential equations into a differential equation of u and x only. Okay, so no more y. All right. So once you know what u is, then you know y is equal to whatever u is minus x, and you get your explicit solution. Okay, so from here, the derivative of u with respect to x is the derivative of this sum. The derivative of x which is 1 plus dy dx. So from here, you know dy dx is equal to du dx minus 1. All right, so with that, you just replace dy dx with du dx minus 1. And then that is sine of, I'm going to write u. By the way, you know, I returned your graded homework, and you make sure you go through your homework and look for my red comments, okay? Because for example, like you have a problem, I think it's like sine of 5x. Don't write like that, and a lot of textbooks write like that too, and that is very improper, because when you write like that, okay, that I would interpret that as whatever sine of 5 is and then times x, all right, by using the order of operations, but that's not, okay? So, you know, if 5x is the angle of the sine function, then you put parentheses around that quantity. Okay.
Wait, sorry, you mean for quiz 3B?
Whatever I graded, I don't remember. I guess so, yeah. The homework that I collected, right?
Yeah, I don't have a grade for it yet.
Well, I returned it.
I also
We
don't.
have it either.
You don't have it?
No, we
No.
don't.
No.
Yeah, I also don't have a grade on it.
Oh, wait, I don't want you to see the grade of all the students.
We have to do that practice quiz that says remotely proctored, or is that to skip?
No, quiz 3B, I graded it already.
I'm talking about the practice quiz.
No, the practice quiz I don't grade.
Oh, okay.
Can you double check if the
For-
3B is published though for us to see?
Let me check real quick. I stopped the share already, right?
Yeah.
Oh, okay. Oh, yeah. I didn't post the grade. I'm sorry. So you can take a look at it later on today. Okay. All right. I just post. Let me see. Yeah. Sometimes. Yes, I posted it. Now, I gave you the practice quiz so you can practice to make sure that you have no problem with Proctorio. But I see only 6 of you taking advantage of that. Right, so just in case you run into some difficulty with Proctorio, you're on your own. Okay. All right. So let's go back. Yeah. So when you receive your homework, if you see a circle, like for example, like in the exercise, if I circle a problem, that means that is the one that I chose to grade. So that problem is worth 5 points. All right. And then the rest of the problems I go through and check and see if you follow the format. It is clear for me to read and understand and so on. That would be 5 points. So you have a total of 10 out of 10. Okay. So take a look at that and pay attention to my comments and try not to do that again next time. All right. Sometimes, like when a homework, usually when there are a lot of homework questions from a particular assignment, then I might just look through all the problems and then give you points instead of selecting a problem or two to grade. Okay. But this time for that particular assignment, I think I don't know. I graded. I think I graded. I graded the one with the partial fractions. I graded problem 17. All right. Okay, let's continue on.
Oh, Professor.
Yes,
So just curious, do we have a quiz for today's class?
of course.
Okay, thank you.
Yeah. Mhm.
And how are we supposed to get those papers back that you chose?
Well, later on, you click on your quiz and you will see I attached that file to that. Okay.
Okay.
All right. So now, from here, you can solve this by separating the variable. So I move the one to the right, like that. And then you can separate the variable. So you have du 1 plus sine of u, like that. And then you integrate both sides. Now on the right-hand side, that's easy. But what about the left-hand side? For the left-hand side, sometimes you try like substitution, you try integrating by parts, you try trick substitution, you try partial fractions, and none of them work. And there is another trick that you learned, I hope your professor taught you, is sometimes you multiply the top and the bottom by something, right? Like how you would do it for integral of secant or cosecant. In this case, you try this trick, which is the conjugate of the denominator. Okay. Now on the right hand side, that's easy. That's just x plus, if you want to, you can just say c, no, that just write c, okay? And then on the left hand side, that becomes 1 minus sine of u over 1 minus sine of sine square of u. So that is 1 minus sine of u. Oops. Over cosine square of u. And then I said, well, how am I going to do this, right? Okay, so if push comes to shove and you don't know how to do it, then you try to simplify the integrand as much as you can. So that is 1 over cosine square, which is secant square. And then sine of u over, okay, so let's do this. So how about, that's what you have. And then minus okay. So the integral of secant square of u du is what? Can you tell me?
Tangent.
Tangent u. Plus
Tangent
e.
of u. For the second one, you would use a substitution. So for that one, you would let u be, I don't use u, I let w be cosine of u. Then the derivative of that is negative sine, the derivative of w is this. Okay, so what I have is the integral of dw over w squared. Now the right-hand side, I still have x plus c. So what I have is tangent of u plus, and that is w to the negative 1 over negative 1. Okay. So everything here is from calculus 2. Minus 1 over w, right? 1 over w. 1 over w, which is 1 over cosine. Okay, so 1 over cosine of u. So to make it look nicer, 1 over cosine of u is secant of u. Wow, okay. What is u?
X
U
plus
is
y.
x plus y. That is my implicit solution of the differential equation, you see? So, you know, like if you really need to show work, there are a lot of steps, right? Okay. So now you can see why some students in this course, they struggle because they don't remember the derivatives and they don't remember how to evaluate integrals. It's not that they have difficulty with differential equations. Differential equations, like I said before, differential equations themselves are not hard at all. Okay, they are very interesting because you see how they are used in real life. But the harder part that makes students struggle in this course is because they don't remember the stuff that they learned in calculus and sometimes in pre-calculus. All right, so that is section 2.5. So now let's go to the last section of the chapter, which is section 2.6. Okay, so let me try to turn on the lights in the room, because maybe sometimes during the daytime when I turn on the lights, then my face is very dark. Hopefully, because the lighting in the background, so now my face is dark, right? Yeah. So. Yeah, I need an extra lamp to put nearby my desk to make the room brighter. Okay, if I turn off the light in the back, then my face is a little brighter. So can you see my face? Okay. All right. So before I lecture section 2.6, let me summarize what we have learned in chapter 2 so far. Okay. So in chapter 2, section 2.1. we learn how to solve differential equations graphically. Okay, that means we sketch a direction field and then we try to estimate a solution curve. Okay, passing through a given point we call initial point, initial value. So that's what we did in section 2.1. Solving solving first order linear differential equations graphically in terms of direction field. And then section 2.2, 2.3, or 2.2, so 2.2, 2.3, 2.4, and 2.5. We have learned how to solve differential equations. We say analytically, or we also say we have learned how to solve those first order differential equations algebraically. That means we actually come up with an exact solution, all right? Whether it is in explicit form or implicit form, all right? Now, section 2.6, we're gonna learn how to solve a differential equation numerically, okay? So there are 4 things that you want to be able to do when you successfully complete a math course. And that is, you know how to express the problem or the result verbally. That means you know how to interpret. Okay, because sometimes students do a problem, they get a solution, but they don't even know what that means or what that is for, right? Okay, so that means you know how to interpret the meaning of the problem or the result. And number 2, you want to be able to learn how to you want to be able to solve an equation graphically. You want to know how to solve an equation algebraically, right? And then number 4, you want to know how to solve a problem numerically. Okay, in real life, solving an equation algebraically almost unrealistic. Okay, because in real life, things are not nice to us. Okay, we don't come across nice numbers. We don't come across a nice equation to solve. So sometimes, most of the times we run into equations that are impossible for us to solve algebraically. Okay, so that's why in calculus 1 you learn how to solve an equation by using the Newton's method, right? Okay, or we call linear approximation and so on. So that is a numerical method to approximate. So for example, if I give you an equation like this, like e to the x equals 3x, and I ask you to solve for x, there's no way you can get an exact answer for x. Impossible. So you can only solve this one graphically. That means you can graph this equation and find out where they intersect. You can use a graphing calculator and find out where they intersect. And wherever they intersect, the x-coordinate right there is the solution of this equation, okay? Or another way is you move this one to the left, and then you use the Newton's method that you learned in section 5, in chapter, I think that's in chapter, probably chapter 3, okay, of the calculus textbook that we are using at EVC to solve. All right. So now you see why when I was in graduate school, I decided to specialize in applied math and also numerical analysis, because I knew that in real life, I needed to know how to solve equations numerically, because it would be unrealistic to just keep solving equations by hand and get an algebraic solution. It doesn't work, okay? So that's what this section is all about. So in this section, we're gonna learn how to solve by using a numerical method, and this is the easiest method involving differential equations, okay? All right, so let me give you a brief overview of what it is all about, okay? So let's say you have a differential equation and an initial condition, okay? Let's say it is solvable. So you're gonna solve this equation, okay? Then that particular solution is phi of x. So let's say phi of x is the solution of this differential equations, all right? When you sketch the solution curve, so in section 2.1, you were able to sketch a solution curve of this IVP by using a direction field, right? Let's say you have a bunch of direction field and you sketch a curve passing through the point x naught, y naught, you get this curve. Okay, that's section 2.1.
Hey, Professor.
Yes?
One of my friends from the class just texted me. He said he just got disconnected. He'll probably be coming back in for a moment.
Okay, that's fine. When they come back, then I know. Okay, thank you for letting me know. Okay, so anytime you get dropped out by your Wi-Fi or your internet, just sign back in, okay? And then I know, because I took roll, so I know that you were here, and you just get kicked out by, I guess, by the internet, so I will put you back in. Okay, so here is the solution curve. So if I ask you, what is the y value of the function y when x is a? You already know what the function is. You just plug a in here and find out, right? Graphically, that y value is, when you plug in a into the function, that is q of a right there. Okay, so let's get that. So that so let's see, which color should I use? So that is q of a, which is actually the exact y value of the function, right? Of the function. Of the function y equals that at a, okay? That is the exact value. But like I said, in real life, we might not be able to solve this differential equation to get the function. So there's no way you can plug a into the function to find out what the y value is, right? So that's not realistic in real life. So the only way, so one way to get that y value is by estimating. So how do you estimate that y value? All right, you can estimate the y value by using the tangent line passing through the initial condition, you see? So when you draw the tangent line, so if you, and because you can find this tangent line easily, because you have a point, you have the slope of the tangent line. How do you get the slope? The slope is actually the derivative at that point. You see, that's from calculus 1. So you can just find out the slope, and you have a point, you can write the equation. So you have the equation of the tangent line. So this is the tangent line. Okay, at this point. We're going to give it a name. Okay, we call it L of x. And the reason why I use capital L is because in calculus 1, you learned a method called linear approximation and also linearization. I don't know if you remember when I say that. Okay, and we use the letter L. Okay, so we use linear approximation. That means we use a line to approximate the y value of a function. Okay, so what we are saying is, what we are saying is, we say the exact value or the y value of the function at a is approximately equal to the y value of the tangent at a, and the y value of the tangent at a is L of a. That is the y value. So we say that is approximately equal to the y value of the tangent at a. Okay. So for this particular case, not always, but for this particular case, can you tell me if your approximation is an overestimate or an underestimate?
In this case, an underestimate.
Do you understand what it means by an underestimate?
It's an overestimate.
An underestimate is your estimated value is smaller than the actual value. Is your estimated value in this case smaller or bigger than the actual value?
Bigger.
Bigger.
So I was looking at
Bigger.
the inverse of it,
Yeah.
rather.
Because your actual value is this y value from here to here. From here to here. But you are saying that that is approximately equal to this y value, which is much bigger, right? So that is an overestimate in this case, not underestimate, okay? So then what is the error? Can you tell me graphically which part is the error?
LA minus QA.
Which is this piece right here, right?
Yes.
Okay. So that is the error. And usually when we talk about error, we talk about a positive value. So we use absolute value around, okay? Because to find the error, you take the actual value minus the approximate value. So when you take the actual value, in this case is smaller than this value, you get a negative number. So you take the absolute value because we always talk about a positive value for an error. All right. So we say phi of a is approximately equal to L of a with an error equals, and then whatever that value is inside the absolute value. All right. So again, this is the actual value of the function of y at x equals a. Okay. And this is the approximate value which is the value of the tangent line at x equals a. Okay. So in this section, we will learn how to approximate the value of a solution at a given x value by using a tangent line. Okay. So that's what we are learning in this section. So in order for us to be able to do that, we need to find out what the equation of the tangent line is, right? So let's try to do that in this case. So in this case, you have a point, you need to find the slope. So you know the equation of the line is y minus the point is x naught, y naught, right? And then the slope. So what is the slope? The slope is actually equal to the derivative of the function, because this is what you learned from calculus 1 at the point x naught, y naught. All right, but what is the derivative in this case? The derivative is the function f here. That means everything on the right hand side, replacing x and y with x naught, y naught. Okay, so that is f of x naught, y naught. Okay. All right, so now we're gonna move y naught to the right side. Okay, plus the slope. And then you have x minus x naught. And we're gonna call this expression right here h. We're gonna call it h. Okay. We call it h. So what do we have? So we have y equals y naught plus h times m, which is f of x naught, y naught. So this is the y here is actually L of x. So that is the linear function representing the tangent line. Okay, so once you have that, then you say L of x is approximately equal to, I'm sorry, phi of x is approximately equal to L of x. Okay, so that's how you approximate. But you see, if you look at the graph, this is a good approximation if the x is near your x naught. Because if it is near x naught, the gap is not that big. But if it is farther and farther away, the error is getting bigger and bigger. You see that? You see when the A here is all the way over here, you see there's a big gap. The error is very big. So you don't want it. You want the error to be small. So if you want it to be small, you want whatever the x value that you want to approximate the y value at, make sure that is near x naught. Okay, so you want to make it noted like for x near the initial x value. Okay. All right. So let's say you are not happy with this error. You want it to be smaller. Well, we can do that. So let's do that. Okay, so in summary, given an IVP, we can approximate the y value at x equals a as follows. You take the y, so the actual y value of the function at x equals a is approximately equal to the y value of the tangent line. We call it L. Line at x equals a. Okay. So that's how you approximate. So the question is, how do you improve your approximation? So this is how we do it. Okay. So let's say here is a. Here is the initial value. You're going to divide it into n number of subintervals. So this is from calculus 1. So from calculus 1, also calculus 2. So so your intervals is, so each one So each one right here is delta x. Okay. And we use the letter h instead. So in here you see h is delta x, which is the difference of the intervals. That means a minus x naught. And divided by the number of subintervals. Okay. And this value right here again, that is the actual value of actual y value. Okay, so actual y value of the solution function at x equals a. Okay. All right. So the way to do that is you divide it into n number of subintervals. By the way, the h here, it has a name. Okay, we call it the step size. All right. So the way to do that is first, see, you're gonna, so you have this line, so you know the initial y value of the tangent line, and then from here you're gonna find the tangent line here, and then you're gonna find out what the y value of that tangent line is at the next x value. So this next x value, see the actual next x value. So the actual value of the solution curve at x sub 1 is this y value, right? But we see in reality, we don't know that red curve. I put it here so you can see the relationship, but we don't know that. So instead, we use the y value of the tangent line, the first tangent line. We use that y value at x1 as if it was the y value of the original solution curve, okay? And then once you have that, then you use this point as your initial point, and then you find the tangent line of that initial point, okay? Passing through that. See, the tangent line passing through the actual point is right here. See, this is the tangent line, but we don't have that. So we're gonna use this point and the derivative and find the second tangent line, okay? And so when you do that, then you use that line to find out the y value at x sub 2 of the tangent line, which is right here. And then we're going to find the tangent line passing through this point, which is like this. See, so when you do that repeatedly, then the very last tangent line is going to be around right there, which is closer to this point, instead of this one when you use only one interval, one subinterval to get, and the gap is very big. But if you do it like this, you can narrow down the error. Okay, so here is how we do it. So first, we're gonna find out y1. Okay, we did that already from here, from right there. That is what we did, right? y1, because we use y1. Okay. So now with x1, y1 right here, you have x1, y1, and then you can get the slope of the tangent line. The slope of the tangent line is dy. Oh, I'm missing the dx. Dy dx at x sub 1, y sub 1. So you plug into the function. So dy dx is right here. Remember that dy dx is f of xy. So at x sub 1, y sub 1, you just plug x sub 1, y sub 1. So you have the slope. So you have a point and you have the slope. You can write the equation. So the equation is y minus y1, x minus x1, and the slope is m, right? And we know that the slope is what? So we have, so now what is, so you have that, and then what is our next objective is to find out y sub 2, right? So you want to find out what y sub 2 is when x is x sub 2. So right here, when y is y sub 2, x is x sub 2. Now, x sub 2 minus x sub 1 is your h, because that is your delta x. That's h. So you know that that is y sub 2 minus y sub 1. The slope is f of x sub 1, y sub 1 times, and this is h. Okay, so that tells you y sub 2 is equal to y sub 2 is y sub 1 plus h times x sub 1, y sub 1. See, so you are able to get the y sub 2 value. So your y sub 2 value is right here. So what you are trying to get is y at x sub n, okay? So our goal is to approximate okay, so this is the y value of the tangent line, of the tangent at x equals x sub n, or basically that's a, right? Okay, so you have to know, so all of the subscripts right here, all of these y's, these y sub i's are the y values of the tangents at x sub i's. Okay, so y1 is the y value at x sub 1, y2 is the y value at x sub 2, and so on. Okay, so you need to understand the process there. All right, so now, so if you continue to do this, so let's say the next point is x sub 3, y sub 3, that's what you want to find, right? So you're gonna use, you have the point x sub 2, y sub 2, then you're gonna find out the slope at x sub 2, y sub 2, and the slope at x sub 2, y sub 2 is f of x sub 2, y sub 2, and so on. So you do that, you see right here, so in general, you have y1 is this, y2 is this. So if you go down here, then you know that y, so this subscript and this subscripts are 1 less than the subscript on the left. So if you have y sub n plus 1, then on the right is going to be y sub n, x sub n, y sub n. But when you write in this case, then you let n be from 0 to 1, 2, 3, and so on. Because when n is equal to 0, you are looking for y sub 1. You already know y sub 0, okay? Because that is your initial condition. Initial condition right here. All right. Okay, so this is the actual, I'm keep writing the actual y value of the solution function okay, at x equals a. That's what it is. And the one on the right is the y value of the tangent line, or the tangent. Okay. At x equals a, all right? Or at x equals x sub n, which is a. Okay. Now, some textbooks, instead of using y plus 1, okay, so here is one way they write that. Or some textbooks you see instead of y sub n plus 1, they write y sub n. But if they write y sub n, then on the right side, it has to be one less, right? The subscript is going to be n minus 1, n minus 1, n minus 1. But then you have to understand now the n has to start from 1. Because if n starts from 0, then you have y sub 0 equals y sub negative 1. We don't have y sub negative 1. We have y sub 0 to start with. So the first y that you're looking for is y sub 1. So you know that n has to start from 1. All right. So here is another formula. So either one is okay. All right. So again, I'm writing. So here, see, so you know y sub a is the actual. So I'm just keep rewriting this because I need to repeat this repeatedly so students know what the difference between these two values is. So that is the actual y value of the solution function at x equals a. And y sub n is the y value of the tangent at x equals x sub n, which is a. All right, I need to make a change up here. Up here is y sub n plus 1 is actually the y value at x sub n plus 1. All right. Okay, so you need to make a change. Let me look at the graph real quick. So it depends on how you label these. Okay, but yeah, okay. So it's n plus 1 equals a. Okay, so what is this one called? That is called the Euler's method. Okay, so that's what this section is all about, using Euler's method to approximate a solution value. Okay, so how do you get the error? So the error we call absolute error, which means it is the absolute value of the actual value at a minus the approximate value. All right. So I prefer using this formula to that one. Okay, so let's not highlight that. Okay, so this one stands out. I prefer using this. Okay, so that is actually like the actual value minus the approximate value. Okay, the relative error is when you take the absolute value, absolute error, and you divide it by the actual value. And when you do that, usually it's going to be equal to a decimal. It's equal to a decimal, right? Okay, and then percent relative error is like you know, is it 1%, 2% error? So to do that is you can just take the relative error, which is a decimal, and you convert into a percent, And you know, in arithmetic, to convert it into a percent, you just multiply it by 100 and then you attach a percent symbol to it. So for example, this could be, say, for example, it could be like 0.025, right? So this would be 2.5%, okay? So that's how you can talk like you know the difference between a relative error and a percent relative error, okay? So let's do one example and then we're done because this section is okay. So remember, if you go back to the geometry behind this, you see when the step size is smaller, you get a better approximation. So the more iterations, that means so for each one like this is one iteration. So the more you calculate, the better the approximation is, okay? It's just like in calculus 2, when you allow delta x, or allow n to get bigger, the number of subintervals is more, then you know that the area under the curve is getting close, the approximate value is getting closer and closer to the actual value when you take the integral, right? So that's what you learn in calculus 2. Okay, so in this case, so you have an initial prom. Okay, so let's identify different things here. So you know that this is your x naught. This is your y naught. And that is your function f of xy. Okay. And this one right here, this 0.2 is your x sub n, which is a. All right. So you have x naught, you have your xn. So this is your x naught right here. This is your x sub n, which is a. All right. Now it says the step size is 0.1. So what you are trying to find is you are trying to find out what. So you are trying to approximate y at 0.2. You want to find out what that is at this. So what is n? Well, let's figure out, let's go to the right side. You know h is equal to a minus x naught all over n. So implies n is equal to a, let me rewrite. It doesn't allow me to move. Okay, so I'm going to do that over here. So you know it's going to be a minus x naught all over h. If you plug everything in, so 0.2 minus 0 is 0.2. 0.2 divided by 0.1 is 2. Okay. So basically what you are trying to do, so right here you go back and you just replace this with x sub 2, right? So this is x sub 2. So that's what you are trying to approximate. So you know when to stop. So that means you divide your interval into 2 subintervals. So here's your entire interval. You divide into 2 subintervals. So you have this as x sub 1, right? So what is x sub 1? So here is 0. Then the next one is going to be 0 plus h. H is 0.1, so that's 0.1. Okay. So you have all of those. So let's get the formula. So from the Euler's method, you know that so y sub 2. So y of 0.2 is approximately equal to. So you write down the formula, right? And this formula is y sub n minus 1 plus h f of x sub n minus 1, y sub n minus 1. For n equals 1, 2, 3, and so on. All right. So that's how you do it. So now you just plug them in. So when n is equal to 1, so n equals 1 implies y sub 1 is y sub 0 plus h f of x sub 0 y sub 0. Okay. What is y sub 0? Y sub 0 is 0. H is 0.1 times f of x. Okay, so you know that. Let's go over here. F of xy is equal to x plus y squared. Now x sub 0 is 0, y sub 0 is 0. So from here, you know that f of 0, 0 is equal to 0 plus 0 squared, which is 0. Okay, so you have 0 plus 0.1 times 0. So you know y sub 1 is equal to 0. All right. Let's go over here. You want to approximate this guy by using this, but this is what? This is actually your y sub 2, okay? Remember, so y of x sub 2 means the y value at sub 2. So you have y sub 1 already, so you have to go to the next step. So when n is equal to 2, you go back to your formula right here. I'm going to highlight this formula so you know that you're going to plug it in here. Okay, so y sub 2, so n is 2, is equal to y sub 1 plus h, f of x sub 1, y sub 1, which is y sub 1 is 0, plus h, which is 0.1. What is x sub 1? X sub 1 is 0.1. Y sub 1 is 0. And then from here, you know that y of 0.1, let me write. You don't have to write every time, but I'm going to write right here so you won't get lost. So f of 0.10 is 0.1 plus 0 squared, which is 0.1. Okay. So what I have is 0 plus 0.1 times f of 0.10 is 0.1. So y sub 2 is equal to 0.1. Okay. So from here, I stop because I know that I just need to get to y sub 2. So therefore, okay, so therefore, y of 0.2 is approximately equal to y sub 2, implies y of 0.2 is approximately equal to 0.01. But be careful, you read the direction. It says problem 2. Let's read the direction. Problem 2. It says obtain a 4 decimal approximation. That means your answer has to have 4 decimal places. Even though 0.01 is the same as 0.0100, but you want to use this because it says 4 decimal places. Okay. All right. Now I'm not gonna do the entire step here, but let's go over here and get the step size. So you know that n. So right here, n is equal. So again, h is equal to a minus x naught all over n, implies n is equal to a minus x naught all over h. So if you plug in A is 0.2 minus 0 divided by this time, the step size, I wrote it wrong. Okay, it's supposed to be 0.05. Okay, it's supposed to be 0.05. So when you do that, what do you have for n? You have 4. That means you're going to divide it into 4 subintervals. Okay, so you have 2, 3, 4. So this is your x of 0, x of 1, x of 2, x of 3, and x of 4. So you know that y of 0.2 is approximately equal to y of x of 4, which is y sub 4. All right. So remember, the y subscripts are the y values of the tangent lines. Okay. And y of an x value, that is the actual y value. So you see right here, the step size is 0.05. So you just keep adding 0.05 to the previous x coordinate to get to the next one. So this is 0.05, add 0.05, you get 0.01, 0.1, and then 0.15, and then 0.2. Okay, so now you can use, the formula. So you know that.
Professor?
Yes.
I don't know how long the quiz is, or how long you are going to give us.
15 minutes. Okay, you have time. Yeah.
Thank you.
So y sub 0.2 is y sub n equals y sub n minus 1. I want to give you the formula right here, and then you can do the rest. Okay. So now you find out what y sub 1 is. Okay, until you get to y sub 4, and you're done. All right. Okay. So just repeat what I just did right here, but now you have to do 4 iterations instead of just 2. Okay. So on the quiz, I give you 15 minutes, but I put more time on there so that Proctorio doesn't dictate my policy. Okay, so technically you have 15 minutes, but I put more time in there so Proctorio doesn't kick you out when you reach 15 minutes, because sometimes I do let students stay for extra time. All right, but make sure you follow my instructions when I call for the quiz. Then you have to submit the quiz. Okay, so I'm gonna stop the share here, and then I will go to Canvas and I publish the quiz, and you should be able to see the quiz now. All right. So quiz 4B, similar to the quiz 2B, is like 5 multiple choice questions. Okay. So please go ahead and get started. And if you're done, submit it, and then I see you next week.